Okay, in this video I'm going to talk about the sham theorem about perpendicular bisectors of the angle bisectors of a triangle. So basically we have an arbitrary triangle, let's say something like this, and we consider the angle bisectors of this triangle. So this, and this. So these two angles are equal, these two angles are equal, these two angles are equal. And we consider now the perpendicular bisectors of this angle bisector. So let's remove this. So each bisector is a segment. So let's say this bisector, we take this segment, we find the midpoint of this segment, and we draw the perpendicular, so like this. This line, let's draw it slightly like this to show that it doesn't necessarily pass through the other point. So this is a perpendicular bisector of this angle bisector, and we consider the intersection point of this line with the opposite side, so this point. And we do the same for the other two bisectors. So we take the midpoint of this bisector, we draw the perpendicular, and consider the intersection point. This and the third one something like this. The intersection point would be somewhere here. And so the theorem states that these 3 points, these 3 intersection points, lie on the same line, on a single line. So so let's denote the points. So A, B, C. Let's denote the midpoints of the bisectors as L, M, and N, and these points of intersection is denoted by so let's denote this point D, this point E, and this point F. And so the theorem says that D, E, F are collinear. Lie on a single line. Yeah, so let's prove this. So I'll draw a separate picture for one bisector, so that not to consider the other elements that we don't need for now. So we have the triangle, we have this bisector, and we take the midpoint of this bisector and consider the perpendicular bisector of this segment and this intersection point. So we denote it by E. So this point is E. So A, B, C. This point was M. So consider that basically what we need to do is now we connect this B and E, and we calculate the angle. So the triangle, so this point is not denoted. Let's denote it by K. Doesn't matter. So observe that the triangle KEB, so it's isosceles, because in this triangle we have, so EM is both an altitude and a median, because like M is the midpoint and it's a right angle. So EM is both a median and an altitude. Therefore, this is an isosceles triangle, and we have the equality of sides. So KE is equal to BE. But what we need is the equality of angles. So this angle is equal to this angle, right? So let's calculate now this angle. So this angle so let's write this. So the angle BK, well, C is correct, but we will need BKE is equal to the angle KBE, right? So so let's calculate this angle BKE, so this angle as the external angle in the triangle AKB. So let's denote the angles of the original triangle as 2 alpha, 2 beta, and 2 gamma. Then this angle as an external angle would be equal to the sum of the two internal angles, the other two internal angles of this triangle. So it's equal to 2 alpha plus beta, right? So this angle is equal to alpha plus beta, BKE. Since it's equal to KBE, so this angle, so this whole angle is equal to 2 alpha plus beta. Also, it's equal to this. But we already have an angle beta here, right? So beta, so KBC is beta. So the remaining, so this part, this part must be 2 alpha, right? So we subtract from 2 alpha plus beta minus beta. So let's write this. So we calculate the angle CBE as the difference between the angle KBE minus the angle KBC. So KBE we just calculated it. It's 2 alpha plus beta, 2 alpha plus beta, and KBC is just beta. So in total we have 2 alpha plus beta minus beta, and this is 2 alpha. So this angle is 2 alpha. So we denote it by 2 alpha. So this angle is equal to this angle. But this means that so in this triangle ABC, in the original triangle, if you consider the circumcircle of this triangle, if we consider the circumcircle of this triangle, we have the angle BAC subtending the arc BC, and this and EBC angle is the equal angle that between the chord and some line. So in this case, like it's a well-known property that in this case this line is a tangent to the circle. So the angle between the chord and the tangent is equal to the inscribed angle subtending the same arc. So from this we conclude, not from this, but from the equality of the angles. Okay, so from this we conclude that the angle A of the triangle is equal to the angle CBE, and from this we conclude that BE is tangent. So if we denote by omega the circumcircle of the triangle ABC, it's tangent to omega. So now, because it's a tangent, so similarly we conclude that the other 2 points, so F and D are also constructed the same way. So not constructed the same way, but they have the same property, that if we connect the point D to A, so basically if we consider here the circumcircle of the triangle ABC, so what we just proved is that BE, if we connect B to this line E, to this point E, it's a tangent to the circumcircle. So similarly, by repeating the same argument, if we connect point D to this to A, and if we connect F to C, they would be also tangents to the circumcircle of to this omega, to the circumcircle of the triangle ABC. So now basically what we have, so let's draw this separately. So what we have is that we have the circumcircle of our triangle ABC, omega, right? And there are these tangents at the points of at the vertices of the triangle. Right? And so the points D, E, and F are the intersection points of these tangents with the opposite sides of the triangle. So we consider the intersection. So this is point E. Was it E? Yes. So this is the point E. This is the point F, and somewhere there, like there is no place on this picture, like somewhere here is the point D. So now we forget about the bisectors and the perpendicular bisectors to them. So all we have is this tangents to the circumcircle and the points D, E, F. And so now basically we observe that so we consider now the intersection points of these tangents. So these points, let's denote it by P, Q, and and this point R. Right? So, and we see that what we have is like so the points D, E, F are the intersection points of the lines containing the corresponding sides of the triangles. So if you consider the triangles ABC and the triangle PQR, right? So the D, E, and F are the intersection points of the corresponding sides of this triangle, of the lines containing the corresponding sides. So E is the intersection point of PR and AC. So AC and PR, right? So F is the intersection points of AB and PQ. So PQ and AB, right? So and D is the intersection points of BC and RQ. So BC and RQ. Yeah, and what we need to prove is that D, E, and F lie on a single line. So, like obviously, this is the setting of the Desargues theorem. So the Desargues theorem says that Desargues theorem says that if we have two triangles, something like this, and then it says that the intersection points of the corresponding sides, so the intersection points of these lines, and these lines somewhere there lie on the same on a single line if and only if the lines connecting the corresponding vertices of these two triangles, so these three lines in this case, if they intersect at a single point. So using the Desargues theorem, we conclude that the collinearity of these 3 points D, E, F is equivalent to the fact that the lines connecting. So by the Desargues theorem, so let's write this, by Desargues theorem, so D, E, and F are collinear if and only if the lines, so the lines connecting the corresponding vertices of these two triangles intersect at a single point. So if and only if AP, the lines AP, BQ, and CR intersect at a single point. Okay, so what are the lines? So the lines AP. So this line. So let's draw it in. Let's draw it in another color. So AP, BQ, and RC. Well, they intersect at a single point because in this large triangle, like in the triangle PQR, this is the Gergon point of this triangle. So these are the lines connecting the vertices of this triangle PQR with the tangency points of the inscribed circle. So this is the Gergon point of this triangle. And it is all like in one of the previous videos, I also proved that this point coincides with the Limoine point of the original triangle ABC. so these lines BQ, AP, and RC are the symmedians of the original triangle. But for the symmedians we don't need it here, so all we need here is that these three lines intersect at a single point, and this follows just from the, well, it follows from the Chevos theorem, and this point is called the Gergon point of the triangle PQR. Yeah, so this line intersect at a single point, so this is true. So this is true because of the, well, yeah, we can say. Okay, so we can write that this is a well-known property. Well-known fact. So this point is called the Gergon point. Yeah, so these three lines intersect at a single point. So it is the Gergon point of the triangle PQ. Yeah, so this holds. Since this holds, so therefore by the Desargues theorem, the EF are collinear. So this basically concludes. So yeah, so from this we conclude that D, E, F are collinear by Desargues theorem. Yeah, and this concludes the proof.